Hello, welcome to Mechan 2040 Solid Mechanics. I am Globas. This is the 5th tutorial of this course, Shear Stress Inside the Beams. For this tutorial, there are 3 major parts which I want to understand. One is the basic concept of shear stress inside the beam, and I have 2 examples to help you to understand the concepts. Besides, we will talk about the longitudinal shear on arbitrary element, but the equation for 5.1 and 5.2 are basically similar. For 5.3, we will talk about the shear stress in the thin-walled beams. In the last tutorial, we discussed about the direct stress inside the beam. It is highly related to the moment acting in each cross-section of the beam. Imagine you have a beam and there is an external torque, external moment acting on it. Then it will compress or elongate the material of the beam, and you also remember that there is a neutral axis. In the last tutorial, we tried to draw the distribution of direct stress by using the moment diagram, because we know that the stress is just the negative of my divided by I. So this is why we use the moment diagram to draw such a distribution. But in this tutorial, all the things are changed. We are not talking about the direct stress, we are talking about the shear stress. So it is very obvious from the name that the shear force diagram will be important. First, let's talk about the shear stress inside the beam. So this is the formula that you are going to learn. The shear stress inside the beam is given by the shear force times the first moment of inertia divided by the second moment of inertia times the width. So tau xy equals to Vx qy divided by Ixx wy, where V is just the shear force inside the cross-section. Q is the first moment of inertia, which I will discuss about it later in the derivation of this formula. Also, Ixx is the second moment of inertia of the entire cross-section about this neutral axis. Wy is the width of cross-section at that particular position of y, so still I will explain to you a little bit later. But all in all, if you are not going to go through the derivation below, then what I can tell you is that the most important thing, the most important formula for this tutorial is tau equals to Vq divided by Iw. So this is the most important thing that you are going to apply in the problems, but in the following I will still try to derive the formula for you. First, let's consider a piece of differential stress element. So for this differential element, it is not something like a cubic one with dx, dy, dz. So it is not something like this. This differential stress element we're going to consider is actually a thin plate. This thin plate has a certain cross-section, maybe like this, but it has a very thin thickness dx. In the derivation of this problem, the stress element we consider is actually a plane with a relatively large cross-sectional area, and we cheat the thickness dx to be very small. This is the only assumption we made. For this thin plate differential stress element, the axial stress distribution on it is linear, as what we derived in the previous tutorial. Sigma equals to minus my divided by I, but we know that sigma will change with respect to x. In the last tutorial, we also tried to draw the distribution of sigma with respect to x, something like this. Now let's consider this very tiny piece of differential stress element, and we magnify it to look it in this way. This piece of differential area element has a thickness of dx, a height of y2 minus y, so bear in mind that y2 is the coordinate of the upper surface of this cross-section, while y is the lower end of this cross-section, so it is not differential, it has a certain length, so bear in mind with that. On both sides of this thin plate stress element, there is direct stresses. On the left hand side, it is minus my divided by I. On the right hand side, it is minus m plus dm times y divided by I. At the same time, we notice that since the direct stress on both sides can be different, That means there must be another force required to sustain the force equilibrium, which is the shear force located at the lower end. The upper surface has no shear force because it is located at the surface. There is no force exerting on it. Now let's talk about force equilibrium of stress element. For this thin plate stress element, notice that it is the side view of it. It has the thickness of dx in the longitudinal direction, while the cross-section of this thin stress element would look like this. It is a possible cross-section. It has a height of y2 minus y. If we further cut the stress element in this way, then for this piece of stress element, it has a width of w, but w is dependent on y because when you shift this differential stress element upward or downward, there will be change. That is, the change of y will change w, so w is a function of y. Then this differential area will become wy times dy. So this is wy, while this is dy. For this thin plate differential stress element, you can see there are two forces acting on it. One is the direct stress caused by the bending on the left hand side. Another one is the direct stress caused by bending on the right hand side. In the last tutorial, we mentioned that we can draw a distribution of direct stress with respect to x, maybe like this, or maybe like this. So in such case, the direct stress on the left hand side may be different from that on the right hand side. Therefore, the variation of direct stress on left hand side and right hand side would cause force in equilibrium. That is, we must add another force to keep it equilibrium. So in this way, since at the upper end of this stress element there is no force, then there must be a horizontal shear force that holds this piece of stuff in equilibrium. So in horizontal direction, there is a shear force VH. Now we consider this piece of differential area dA, where dA equals to wy dy. Then for this differential stress element, its dimension will be dx times dA, which is dx times dy times wy. In another word, the differential force acting on it will become dF equals to sigma dA. The reason is that on the left hand side and the right hand side, it is given a stress distribution on the surface, and the force is given by the integral, the summation of the stress and the differential area. So we can say for this piece of differential area, the differential force acting on it will become the local stress, sigma, times the differential area, which is given by wy dy. Then the net force on the left hand side surface and the right hand surface can be given by integrating this differential form on the left hand side and right hand side. On the left hand side, sigma x equals to minus my divided by I, and we know that dA equals to wy dy. Further, we know that since we are integrating with respect to dy, we are interested to the range of y, but it is clear that the range of y is from y to y2. Therefore, we just write the integral of y to y2 to get the net force on the left hand side caused by the bending, which is F1. Similarly, for F2, the stress given by bending is minus m plus dm y divided by I. dA equals to wy dy. We integrate this from y to y2 to get the net force on the right hand side caused by the bending on this differential stress element. Now we have F1 and F2. Then we consider the shear force acting on the stress element, which is this force. For this force, it is exerting on a surface of thickness dx, or the length dx, and the width wy. So imagine it is a stress element. You have a thin plate stress element. F1 looks like this, F2 looks like this. The thickness is dx, the width is wy, the height is given by y2 minus y. Then what is the area of this surface? Recall that this surface equals to the lower base. So those two surfaces has the same area. So what is the area? It is given by dx times wy. Therefore, the shear force acting on this surface is given by the shear stress times the differential area. Vh equals to tau h times dA, where dA equals to wy times dx. Now we have all those things ready, and by the force equilibrium, we know that F1 minus F2 minus tau h equals to 0. Then we substitute all those forces as well as this one into this equation. Next, we try to simplify it by observing that the my divided by I term can be cancelled out. Then the things left here is y dm divided by I times wy dy integrated from y to y2 minus tau h wy dx equals to 0. This equation seems a little bit strange because, okay, why there is dm and a dy existing in the same integral, and why there is a dx existing here. So don't worry, there is a way that we can do it. We divide both sides by dx. The left hand term will become the integral from y to y2 dm dx times 1 over I times y wy dy. And for the right hand term, you just cancel the dx out. That's it. So those two stuff, since they are irrelevant to y, then we just take them out to be the constant. Then the equation can be written in this form. If you have read our tutorial notes carefully in the last tutorial, we mentioned a very important relationship, which is the shear force equals to the differential of moment with respect to x. That is, v equals to dm dx. Therefore, this term is simply becoming the shear force acting on this cross-section. Besides, since we know that dA equals to wy dy, we can write this wy dy to be dA with respect to an area. One important observation is that the area you want to integrate with is actually come from this lower and upper limits. So this lower and upper limits give you the hint that you should integrate the area which is above the level of y of this cross-section. So in the later examples, you will see the application of this formula and how do we compute it. Another observation is that this integral is rather familiar, right? We introduced in tutorial 0 that it is the first moment of inertia with respect to the horizontal axis, which is qx of y. So in the later stage, you will do some examples that you will find the first moment of inertia above a certain level of y for some problems. So you may see those things later. So now this equation is becoming 1 divided by I times v times q minus tau w equals to 0. Then we can rewrite this equation to be tau equals to vq divided by iw. It is still talking about the horizontal shear force. So now we get a conclusion that the horizontal shear stress inside the beam is dependent on two variables, x and y. It equals to the shear force acting on this cross-section times the first moment of inertia of an area above the level of y divided by the second moment of inertia of the entire section times the width of that particular height, particular value of y. So now you can see the horizontal shear stress is dependent on two variables. But no worries, we can simplify all those things quickly. The first observation is that the vertical shear stress is equal to the horizontal shear stress. Then tau h is just becoming tau. Also, the shear force inside the cross-section is just the shear force, which is v. Then this will become v. The first moment of inertia, we just use another notation, we simplify it. It is just q. For the second moment of inertia, actually there is nothing worth us to simplify. You just bear in mind that this moment of inertia is evaluated with respect to the horizontal axis. the width of the cross-section at a particular position y is just W. Finally, you will get this very important shear formula, tau equals to VQ divided by IW. So if you didn't go through the proof I just went through, then you would have trouble to understand all the terms inside this formula. What is tau? What is V? And especially what is Q? So Q is a very strange quantity that you need to think of it. And the moment of inertia, I believe you have already learned how to compute it in the previous tutorials. W is the width. So after going through all those proof steps in the previous slides, I believe you are now familiar with this equation. But still, recall some major restrictions regarding to the use of this equation. It is only useful for axially symmetric cross-section. So recall that for this direct stress formula, in the last tutorial, we tried to write a general version which is applied to all the cases, all the cross-sections. So the general version is given by sigma c equals to minus mx Iyy minus Ixyx divided by Ixx Iyy minus Ixy squared minus my Ixxx minus Ixyy divided by Ixx Iyy minus Ixy squared. So we described such a formula in the last tutorial for you to challenge, or anyway, it is something in year 3, but there is such a formula, and unless you make this cross-section to be axially symmetric, then Rxy is non-zero, then this direct stress formula will become much more complicated, and this derivation will be not that simple. Besides, another important point we need to point out is that this equation just gives an average shear stress across the width. The shear stress is actually non-uniform across the width in the real case. So let's visualize the derivation we just went through and try to do some simple review on the derivation. So consider this piece of bar which is under a loading, a moment exerting on this bar. Then we pick up a differential area element. This is a thin slice of plane. This is a very thin slice of plane with the thickness dx, as well as the height of y2 minus y and the width of wy. So in this case it is special because I chose a rectangular beam, so this is why the wy can be treated as constant. But anyway, let's see. So for this differential stress element, there is direct stress F1 and F2, which is linearly distributed on the left hand side and right hand side. At the same time, there is a shear force tau h acting on the lower end of this differential stress element. So recall that on the left hand side, sigma x equals to minus my divided by I. On the right hand side, sigma x plus dx equals to minus m plus dm times y divided by I. Then we can do some integration to find f1, f2. So here we pick up a very tiny slice of differential area element, dA. So it is the height of dy, the width of wy. For the left hand side, df equals to minus my dA, which is wy dy. On the right hand side, df equals to minus m plus dm y divided by I wy dy. Then we know f1 equals to the integral from y to y2 minus my divided by I wy dy. f2 equals to minus y to y2 m plus dm y divided by I wy dy. And vh equals to tau h times wy dx. So we do the force equilibrium of those three forces, then we can get the result. So the force equilibrium for those three forces are left to you as an exercise. I'm not going to continue. Recall that the shear formula we just introduced before just gives an average of shear stress across the width. Our concentration is to find the shear stress located at position Y. So here is Y, it is Y2, okay? At position Y, if we consider this cross-sectional area and we compute the first moment of inertia of this cross-sectional area, then we can find the average shear stress acting on the level of Y. It is not talking about the shear stress acting on the entire cross-section, it is not. It is just talking about the shear stress acting through the width of this cross-section at position Y. The stress distribution profile is often parabolic, like what is shown in this figure. Now let's do some example. It is a past lecture example, and I modified a little bit such that you need to do some sketch of distribution of average shear stress. A simply supported beam is under an external transverse load P applied in the midsection. Sketch the shear force diagram along the length of the beam as well as the shear stress distribution along the length of the beam for points A, O, and B. So it is talking about the points of A, O, and B of the cross-section. Probably there is some overlap of use of letters, so bear in mind with that. So A and B in the left figure is talking about the tips, the pin and the roller support, while the AOB in this cross-section is talking about a point in the cross-section. Besides, we also need to sketch the distribution of average shear stress along the transverse direction of the cross-section. First, we try to sketch the shear force diagram along the length of the beam, which is very easy. If we cut the beam between 0 and L/2, so we cut the beam here, then by sign convention of the beam, the shear force inside the beam is Vx equals to P divided by 2, because it is significant that the two supports are both given the load of P/2. So for the left section, the Vx is P/2, and if we cut the beam on the right hand half like this, then the shear stress inside the beam will become minus P divided by 2. Then we can sketch the shear force diagram along the length of the beam like this. It is quite simple. Next, you are required to sketch the shear stress distribution along the length of the beam for those 3 points. So the second moment of inertia of this cross-section, which is very easy to compute, we compute a lot of times in the previous tutorials. It is given by the width times the height cube divided by 12. The width of the cross-section at any position is given by W. Because it is rectangular beam, the width is uniform across the vertical direction. In the previous slide, we found that the distribution of shear stress is given by P divided by 2 for the left half and minus P/2 for the right half. So at this moment, we confirmed 3 items. One is the second moment of inertia, another one is the width, another one is the shear force applied in this cross-section. So we confirmed those 3 quantities. Recall that our equation is tau equals to VQ divided by IW. So what we need to do now is to determine what is Q. However, what I want to tell you is that in this tutorial, the quantity Q is one of the most important, one of the key factors for the determination of the shear stress. In this example, you will see at point A, we only compute the region above it. So still recall that just now, when we derived the formula, what is our lower and upper limits? And after we find the first moment of inertia, what is the shear stress we found? The shear stress we found is actually the shear stress at the level of Y, right? Y is here. And what is the first moment of inertia we found? The first moment of inertia is just the region above the level of Y. So now at point A, Y equals to h divided by 4 and y2 equals to h divided by 2. Then the first moment of inertia evaluated for this region with respect to the neutral axis is given by q equals to the double integral of y dA, but dA equals to dy from h over 4 to h over 2, and the dz is equal to w So what I mean is that the width, no matter where you take the integral, will always be w. So actually you can take this thing out to be w. Then we compute this first moment of inertia, and we get 3wh squared divided by 32. Actually, still remember that in the previous tutorial, we didn't use the integral to find the first moment of inertia. Actually, for the rectangular region, there is another way to find the first moment of inertia, which is we first find its area. So the area of this shaded region, the region of interest, is given by WH divided by 4. Then we try to find the distance between its axis of symmetry and the neutral axis. So for this region, its axis of symmetry has a distance of 3h divided by 8 with respect to the neutral axis. Then it is 3h divided by 8. By multiplying those two terms together, you will also get the same answer, which is 3wh squared divided by 32. At point O, rather similar. First, we'll find its area, which is WH divided by 2. Also, the axis of symmetry of the shaded area has a distance of h divided by 4 with respect to the neutral axis. Therefore, the first moment of inertia of the shaded area is given by WH squared divided by 8. At point B, the area is given by 3wh divided by 4, and the distance of the axis of symmetry of the shaded area with respect to the neutral axis is given by h divided by 8. The first moment of inertia is given by 3wh squared divided by 32. So just now we determined V, I, and W as well as Q. Then the average shear stress at the level of A, level of O, and the level of B can be found by using the shear formula. Still recall that the shear stress found in this way is an average across the width. So across the width, there could be a parabolic distribution as shown in the previous slide, okay? So it is just an average. Recall that, it is just an average. After that, for point A, we found the average shear stress when V is positive is given by 9p divided by 16wh. At point O, it is given by 3p divided by 4wh. And at point B, it is given by 9p divided by 16wh. Finally, we can draw the distribution of shear stress along the length of the beam. For point A, first it is 9p divided by 16wh, but after L divided by 2, the shear force V will become minus, then consequently the shear stress inside it will become minus as well. This is why, for the first half, for the left half of this beam, the shear stress is positive, which is 9p divided by 16wh. But for the right half, the shear stress is negative, which is minus 9p divided by 16wh. And similar for O and B. Next, we are required to sketch the distribution of average shear stress along the transverse direction of the cross-section AA, which is located at the left half of this beam. Now we have V, I, and W are all constant. Then the first moment of inertia of a region above a point located at an arbitrary altitude y is given by this. So how can we get that? So consider a piece of shaded area. This cross-section has a width of w and a height of h. This is the neutral axis, which means the upper end is given by h divided by 2 and the lower end is given by minus h over 2. The position of the axis of symmetry of this shaded area is given by y plus h divided by 2 divided by 2. So it is written here. The height of the shaded cross-section is given by h minus 2 divided by y. It also has a width of w, which means the area of the shaded region is given by h divided by 2 minus y times w. So multiplying all those things together, we can get the first moment of inertia of the shaded region with respect to the neutral axis, which is w times h divided by 2 minus y times 1/2 of h divided by 2 plus y. Since the moment of inertia is given by wh cubed divided by 12, we substitute this value or first moment of inertia into our shear formula, which is located here, here, and here. So notice that we absorbed W and 1/2 into this term. Now we do some cancellation regarding to this shear formula. We know that this W can be cancelled with this W. Then the denominator only has WH cubed remaining. But we know that the cross-sectional area of this cut surface is given by WH, which means we can rewrite the WH cubed to be AH squared. Then we further simplify this expression by taking h squared divided by 4 out from this bracket. Then we get the result, which is 1.5 times v divided by a times 1 minus 4y squared divided by h squared. So what does that mean? V divided by a is the average shear stress acting on the cross-section. The maximum shear stress occurred on the neutral axis. The reason is that in order to maximize this equation, we want to make this term to be 1, and the only way that we can do that is to make y equals to 0. The magnitude of the maximum shear stress is 1.5 times of the average value, as what we can observe from this formula. Also, since the average shear stress in the transverse direction is a function of y, and we observe that y is quadratic, therefore we conclude that the distribution of the shear stress is parabolic along the transverse direction. This is actually a concept introduced in the textbook and your lecture notes. You can find the distribution of the shear stress here. So this is the distribution of the shear stress inside the beam along the transverse direction, and it is parabolic and is given by this equation. Next, let's talk about the vertical nails. It is the nail spacing problem. I found this problem online because when I do this PowerPoint, I also don't understand what is the nail spacing, so I searched the internet. And I found such a kind of problem, an example that worth you to try it out. The nail spacing is 100 mm along a beam with the x-section shown below. The shear force allowed per nail is 1200 newtons. Find the maximum allowable shear force, Vmax, that can be exerted on this beam. The cross-section is given in this form, and the nail spacing is actually in this form. To help you better visualize this problem, I tried to draw such a kind of box beam in the SolidWorks. This beam has a width of 260 millimeters, and for the upper flange and the lower flange, the thickness is 25 millimeters. For the webs on the two sides, their thickness are 50 millimeters. So bear in mind that if we have a box beam, the horizontal structural elements are called flange, and the vertical components. So in the rest of the tutorial, I will just follow this nomenclature, the flange and the web, to tell you about the concepts. So bear in mind with that. Still, the nail spacing is actually, in general, not shown to you because the engineers, the booksellers, suppose you know what is the meaning of nail spacing, but for us, quite a lot of you may not really know what is the nail spacing. So we know that the beam is actually a very long item. A beam sometimes is fixed like this, right? But for this kind of beam, there are 4 pieces of wood which are joined together by using the nails like this. Otherwise, it is impossible to make this beam stable. You must use the nail to keep it, right? But it is impossible that you put the nail everywhere along the length, like this, this. That is crazy and insane. It is impossible that you put infinitely many nails on the beam to keep it stable, right? But at the same time, you also have to consider how many nails you need to put. How can I save the usage of the nails? And whether this amount of nails can hold the structure stably. So all those things are to be addressed in this example. Since we are going to find the maximum allowable shear force, first we compute the sectional properties. The second moment of inertia I about the z-axis is given by the outer rectangular region minus the inner rectangular region. For the outer rectangular region, it has a width of 260 and a height of 310. Then, the moment of inertia of the outer part is given by 1/12 of 260, 310 to the power 3. For the inner rectangle, it has a width of 160 and a height of 260. Therefore, the moment of inertia of the inner rectangle is given by 160 times 260 to the power 3 divided by 12. After you're doing a series of computation as well as converting the unit mm4 to the meter to the power 4, then you will get the second moment of inertia I of this cross-section with respect to the z-axis or the horizontal axis, which is 4.11125 times 10 to the power minus 4 meter to the power 4. Then we need to compute the first moment of inertia above the level of the nailed boundary. So remember, we nailed this beam because we want to fix those two pieces together, right? So the major source of shear force exerting on the nail will be the boundary, because for the nail section inside the material, the shear force is evenly distributed, or in the tutorial 1 we also talked about the bearing stress. So it is not that large, but for the shear stress, for the shear force acting on this nail on the boundary, it could be large and it will cause the damage to the nail. Therefore, we need to take the consideration of, and we are interested to the first moment of inertia of the region above this boundary. For the region above the nailed boundary, the area is given by 25 times 260, while the distance from the neutral axis to the axis of symmetry of this area, of this region, is given by 130 plus 1/2 of 25, which is 12.5. So it is like this. The first moment of inertia of the region above the nailed boundary is given by 9.2625 times 10 to the power minus 4 meter cubed. Here, let's introduce a concept of the horizontal shear force as well as the nail spacing. The shear stress in the horizontal direction is the major concern of this problem instead of the vertical one, okay? The shear flow formed by the horizontal shear stress at the same level of y is given by Q equals to VQ divided by I. You can see that tau equals to VQ divided by IW and Q equals to VQ divided by I, which means Q equals to tau times W. And if we further our dimensional analysis, tau is in the unit of Newton per millimeter squared, maybe, okay, and the width has a unit of millimeter, which means the unit of Q will become Newton per millimeter. So this is the concept of shear flow, and we also introduced it in the previous tutorial, so you can refer to section 3.4 for more information. But that one is for torsion. In this case, we are just talking about the pure bending, the shear flow, the shear stress caused by the pure bending, okay? On the same level of the nailing boundary, the shear flow is given by VQ divided by I. That is, the shear flow is really like a flow that is flowing in this direction and trying to give a shear force to the nail. But what is the magnitude of the force? So the horizontal shear force is given by Q times S. So still, Q has a unit of Newton per millimeter, and the spacing S has a unit of millimeter. Eventually, you will get a force like this. That is, the shear flow in this section will try to rush to the nail located in this position and then cause a shear force acting on this nail. Besides, since there are two nails located on the same level, so those two nails are resisting the shear flow at the same time. Therefore, 2 times the allowable shear force of nail is the horizontal shear force, and the horizontal shear force equals to the shear flow times the spacing. But you know that the shear flow is just VQ divided by I. Then we can write 2 times the allowable force of nail equals to the shear flow times the spacing, which equals to VQ divided by I, which is the shear flow, times the spacing s. Based on this equation, now we can find the expression of the maximum allowable shear force, Vmax. It is given by 2If divided by Qs. So still, 2F equals to VQS divided by I, then 2If equals to VQS, then V equals to 2If divided by Qs. But we know what is I, we know what is the allowable force of nail, F, we know what is the first moment of inertia, Q, and it is also given that the nail spacing is 100 millimeters. Then the maximum shear force allowed for this beam is given by 10,650 newtons. So in the very beginning of this tutorial series, maybe I have already shown this picture to you before. So this bolt is failed because of the shear stress, the shear force. So on the left hand side there might be a shear force like this. At the same time there is another shear force acting here. So those two parts are kinds of distribution of shear force and cause relatively small impact to the nail. But for this section, in case those two distributed loads are different, then there will be a shear force located in between. For this section, I guess there is an overwhelming shear force at this section that made this bolt fail. So it is also the failure mode of the nails inside the box beam, as was shown just now. So for this box beam, there is a distributed load like this, and then at this horizontal surface there is a shear flow, which is providing a relatively large shear force to this nail. And for the nail below this boundary, there is also a distribution of shear stress. Next, let's consider a stress element of arbitrary shape cut from the beam. So in the previous case, we tried to account for all the region above the level that we concern. So for example, we have y and the y2, then we account all the region above the level of y. But in this case, we only take a tiny piece of area, and it is an arbitrary shape. It is not like this, okay? We are not accounting all the area above the level of y. Instead, we try to account some region above the level of y, and we observe the horizontal shear force, the two direct stresses on the left hand side and the right hand side, and the force equilibrium stuff. So still, we only consider the horizontal forces exerting on the stress element. For this stress element, it looks like this. Hope that you can feel comfortable with this drawing. The stress element looks like this. It has a distribution of F1 as well as a distribution of F2. At the same time, at the bottom of this stress element, there is also a horizontal shear force, delta H. I hope this drawing is acceptable to you. So we only consider those horizontal force components. Then we get delta H plus delta C minus delta D, dA equals to 0. Consequently, by very similar derivation process, we can get delta H equals to VQ divided by I times delta X. So the derivation is rather similar to what we introduced before. So still left to you as an exercise. It is very similar. If we try to divide both sides by delta X, then the left hand side will become the shear flow, and the right hand side is VQ divided by I. So still, you might wonder, why am I teaching you the same thing? So just now, I taught you what is the concept of shear flow. The equation was Q equals to VQ divided by I, but here you teach this formula Q equals to VQ divided by I again. Why? It is because there is some new meaning in the letter Q. The letter Q here is the first moment of inertia of the shattered area, which is the arbitrary region above the position of y only. So in the previous section still, we talked about the first moment of inertia for the entire region above y. But this time, we don't consider the entire region. We just consider an arbitrary region, say A, like this. So in this case, the shear flow formula is still work. And we can also adopt this formula to solve some problems. Just now, we dealt with the problem of vertical nails. But how about the horizontal nails? What are their difference? So in this problem, we are going to explore this stuff. Two wood box beams, A and B, they have the same outside dimensions, which are 200 mm times 360 mm. All the members of those beams has a thickness of 20 mm. Both beams are formed by nailing, but for beam A, it is formed by the vertical nail. For beam B, it is formed by the horizontal nail. Each nail has an allowable shear load of 250 newtons, and the beams are designed for a shear force V equals to 3.2 kilonewtons. So this time, V max is given to be 3.2 kilonewtons. What is the maximum longitudinal spacing, SA, for the nails in A? And what is the maximum longitudinal spacing, SB, for the nails in beam B? And then you are going to comment which beam is more efficient in resisting the shear force. For the A part of this problem, it is very similar to the previous example because it is vertical nail. We need to evaluate the first moment of inertia for the region above the nailing boundary. First, evaluate the second moment of inertia, I. It is given by 3.4 times 10 to the power minus 4 meter to the power 4. And the first moment of inertia of the region above the nailing edge, here, after a series of computation, it is given by 6.8 times 10 to the power minus 4 meter to the power 3. Then we can compute the shear flow by substituting all those numbers into this equation. The shear flow is given by 6,387 Newton per meter. Since two nails located here are resisting the shear flow, and the force exerting on each nail is given by the shear flow times the spacing, then we can write 2 times the allowable force of nail equals to the shear flow times the maximum spacing. Then the maximum spacing is given by 2 times the allowable force of the nail divided by the shear flow, which is 78.3 millimeters. For part B, it is talking about a horizontal nail, but the computation of first moment of inertia would be different. So let's observe the difference of the region used to compute the first moment of inertia. We can see that the region used is like this. I don't know how to express it in words, but you can see the difference between A and B. So the first moment of inertia is given by 160 times 20 times 170, which is 5.4 times 10 to the power minus 4 meter cubed. The shear flow is given by this, by substituting all those known informations. Then the maximum spacing is given by 97.9 millimeters. By comparing those results, we can see that the maximum spacing for beam B is larger than that of A. A conclusion can be drawn that since beam B has a larger maximum spacing, it allows to reduce the density of the nails used on this beam, and consequently you don't need to use too many nails on a beam. Therefore, beam B is more efficient in resisting the shear force. Finally, let's discuss about the shear stress in the thin wall sections. Consider a slice of cross-section like this, the I-beam, and we further cut this piece of I-beam, and we only consider this very tiny piece of stress element. It has a horizontal shear force, delta H, which equals to the shear flow times the length, which is delta X. But the shear flow is VQ divided by I, then the horizontal shear force is given by VQ delta X divided by I. This slice of area element has a thickness T as well as a length delta X. That means the average shear stress inside the slice of area element is given by F divided by A. Force is just the delta H. The area is given by T delta X. That is, the average shear stress is given by VQ delta X divided by I, then divided by T delta X. Then we do a lot of cancellations. Finally, we can get the average shear stress in a thin wall section is given by tau average equals to VQ divided by IT. So all things changed is just T and W. So just now we know that tau equals to VQ divided by IW, but here we just replace it by T, then that's all. This is a past homework problem that worth you to have a try. A hollow steel box beam has the rectangular cross-section shown in the figure. Determine the maximum allowable shear force V that may act on the beam if the allowable shear stress is 36 MPa. Firstly, the maximum shear stress is talking about the shear stress in the midsection, because in the midsection, the first moment of inertia is the largest. So just now, for a rectangular beam, we know that there is a shear stress distribution which is parabolic, and the maximum is in the middle, right? So in this thin wall case, the maximum shear stress also occurs in the midsection. It's located in the middle of the section. The reason is that the first moment of inertia evaluated in the middle is always the largest for the symmetric rectangular beam. You may want to verify this phenomenon yourself. The first moment of inertia evaluated for the section above the middle, which is here, the first moment of inertia evaluate is given by 1.28025 times 10 to the power minus 3 meter cube. And the second moment of inertia of this cross section is given by this. So I don't tell too much, just leave you as an exercise. Now we have the maximum allowable shear stress, tau max, as well as Q and I. The thickness of beam in the middle section is given by 20 mm. The reason why we say 20 is that we consider the first moment of inertia of the entire region above the neutral axis. Then we will also account the thickness of both the webs, which is 20 mm. Finally, we can find the maximum allowable shear force, V, that can be exerted on this box beam, which is given by 36 MPa times the second moment of inertia as well as the thickness, divided by the first moment of inertia evaluated in the middle. The maximum shear force is given by 272.72 kilonewtons. Let's do some simple summary about this tutorial. We talked about the shear formula, tau equals to VQ divided by IW. We also talked about the shear flow, Q equals to VQ divided by I. We also talked about the relationship between the nail allowable force Fn as well as the shear flow and the maximum spacing. So remember, the allowable force of the nail equals to the shear flow times the spacing, because the nail is going to resist the shear flow, you can imagine. Since shear flow equals to VQ divided by I, then you can place this equation here to get the equation, which is Fn equals to VQS divided by I. You can find whatever you want if you know 4 of those unknowns. Finally, we also talk about the shear stress in the thin wall beams. The average shear stress is given by VQ divided by IT. After all, for this tutorial, you would find a very important phenomenon that the first moment of inertia Q plays an important role in the determination of the shear stress. The larger first moment of inertia, the larger shear stress on that level of Y. So this is the end of the tutorial. In this tutorial, there were 4 examples that are carrying different amount of marks. And the total mark is 95, and the following tables are for your self-evaluation. Those grades are for your reference only, and I don't responsible for the inaccuracy, because as a student, you also need to be responsible for your own grade, your own performance in the exams. Finally, thanks for watching, and see you in the next video.